In this video, we shall solve a few problems associated with potential energy. Problem 1. An object with mass 3 kg, so that is this mass right there, is dropped so that a person who stands on the ground 8 meters below can catch it. If the person's hand level are at a distance of 1.4 meters above the ground, note above the ground, find the work by gravitational force on the object as it drops to the person's hands. So let's do part A. We want to determine the work done by gravitational force. Now we know the work done by the gravitational force equals the gravitational force, in this case the weight, dotted into displacement, let's call it y. Now the motion is in the vertical direction, so if the upward direction is positive y-axis, the downward motion is parallel to the minus y-axis. So the unit vector along the y-axis is j hat, so minus y-axis is minus j hat. So what is the gravitational force acting on this object? The weight, that is. And it is quite simply the mass 3 times gravity. So the work done by gravitational force is 3g in the direction of minus j hat, because gravity always acts, or the weight always acts downwards, dotted into displacement. Note, as the object falls, it falls that much distance. So that distance is 8 minus 1.4, which is 6.6 meters. So the displacement in a downward direction is minus 6.6 j hat. So minus j hat dotted into minus j hat is 1. 3 times g times 6.6 will give you 194 joules. And this is positive 194 joules. Now we have taken the g to be 9.81 meter per second squared here. Let's do part B. What is the change in gravitational potential energy of the object Earth system during the drop? Now the change in potential energy is the final potential energy minus the initial potential energy. Now that level is the final level, and the level from which it drops is the initial level. Now we are going to set the potential energy at ground level to be 0 joules, because we need to set it to be 0 somewhere. Let's calculate what this UF is, the final gravitational potential energy. The final gravitational potential energy is given by the expression mgh. So m is the mass, 3 kg, gravity is 9.81, and h is measured from that level, the ground level. And in this case, it's quite simply 1.4 meter. The initial potential energy is again 3 times the mass times gravity. Now the entire height, this height, which we know to be 8 meters, and the difference will give you the change in the potential energy, which is minus 194 joules. You may note that the answer computed in part A, namely the work done by the gravitational force, is minus the change in the potential energy of the object Earth system. Now this is the property of the so-called conservative force. So in this case, the conservative force is the gravitational force. Now let's do part C. If the potential energy is taken to be 80 joules at the ground level instead, find the change in the gravitational potential energy of the object Earth system now. So now, the potential energy at the ground level is not 0, but we are setting it to be 80 joules. So you do the same thing. The change in the potential energy is the final potential energy minus the initial potential energy. The final potential energy is the potential energy at that level. So it is the mass times gravity times 1.4 meters. Do not forget to add 80 because now all the energy levels have been raised by 80 joules. So that is the final potential energy. The initial potential energy likewise is 3 times gravity times 8, because initially the object is there at a distance 8 meters from the ground, and plus 80 because all the energies have been raised by 80 joules. And you see that you're going to get the same answer as part B, 194 joules with a minus sign. So this problem shows where you set the zero level is immaterial. What's important is just the difference in the potential energy, because that is what controls the physics of the system. Let's look at this problem. In figure below, a mass 4 kg is attached to a thin, massless rod with length 2 meters. So that is the rod in red. The other end of the rod is pivoted so that the rod with mass swings freely on its vertical plane, like that. The rod is pulled and released from rest. So the rod is pulled up to an angle of 28 degrees from this vertical line and then released. As the mass descends to the lowest point, so that is the lowest point, calculate the work done by the gravitational force on the mass and also the change in the gravitational potential energy of the mass Earth system. So the work done can be computed in a similar manner. So work done by the gravitational force equals the gravitational force, in this case the weight of that mass, dotted into the vertical displacement. Now we know the weight acts like that, and that is the gravitational force. It's 4 times gravity. Now the displacement as the object moves to the lowest point is that. So let's call it y. Now we can calculate what y is, because y is quite simply this entire length, which is L, subtract that length, which is L cosine 28 degrees. And in this case, L is just 2 meters. So let's put everything together. Gravitational force is acting downward, so it's minus a 4g j hat. Minus j hat is the direction of that downward gravitational force, dotted into the displacement. Displacement is also downward with a magnitude of L minus L cosine 28. Now we know what L is. L is 2. 2 minus 2 cosine 28 degrees in the direction of minus j hat. And the answer is plus 9.2 joules. Note, minus j hat dotted into minus j hat is 1, and the rest will give you 9.2. Part B. Find the change in the gravitational potential energy of the mass Earth system. Remember, we have the freedom to choose the 0 joule for gravitational potential energy at some point, and I'm going to choose the 0 joule at the lowest point. So what that means is the lowest point is the final point, and that is the initial point. So in determining the change in gravitational potential energy, you take the final gravitational potential energy minus the initial gravitational potential energy. The final gravitational potential energy has been set to 0. The initial gravitational potential energy, namely the gravitational potential energy of the system when the mass is there, is given by the mass, which is 4 kg, gravitational acceleration g, and the height from the 0 level. In this case, let's call it y, and we know what y is. It is 2 minus 2 cosine 28 degrees. Again, this entire thing is 2, and this is 2 cosine 28 from simple trigonometry. Note that we have a right angle triangle. This is 28 degrees. This is 2. So this length must be 2 cosine 28 degrees. And the answer you will get is minus 9.2 joules. As expected. So as you can see, this is a conservative system. So the work done on this object is the same as minus the change in the potential energy of the system. A third problem. The only force acting on a particle is a conservative force, F. At some point C, the potential energy of the system associated with that force is 55 joules. Now, if the particle moves to another point, say D, the work done by the force on the particle is now plus 20 joules. Find the potential energy of the system with the particle at point D. Now let's assume the object or the particle is moving from point C to point D. The potential energy at point C is given to be 55 joules. That's that number. We don't know what the potential energy at point D is. That's what we want to determine. However, we know the work done in this process by that force F, and that is plus 20 joules. Now this is a conservative system, so we know work done is minus the change in potential energy. Minus the change in potential energy means minus the final potential energy minus the initial potential energy. So in this case, the final potential energy is the potential energy at point D, and the initial potential energy is the potential energy at point C. So you see you get UC minus UD is the work. So let's substitute the numbers. The work is 20 joules. It's plus 20 joules. UC is 55. UD we don't know. So you can figure out UD, and UD is 55 minus 20, and that is 35 joules plus 35 joules, and that's the answer. Let's look at the last problem. A 2 kg ball, so this ball is 2 kg in mass, shot upward with a projection angle of 38 degrees to the horizontal with an initial speed of 25 meter per second. Calculate its initial kinetic energy. So now that is simple. The initial kinetic energy is half, the mass is 2, and square of that speed, which is 25 squared, and that's going to give you 625 joules. Now part B. Calculate its kinetic energy at the highest point. Now when the object reaches the highest point, the velocity is purely to the right. So the speed at that point is quite simply 25 cosine of 38. The x component of the velocity it had at that point, because the x component does not change. So the final kinetic energy can be computed half times mass times 25 cosine 38 degrees squared, and that will be about 388 joules. Now part C, find the change in gravitational potential energy as it moves from the launch point to the highest point. Note that we are dealing with a conservative system. That means the change in potential energy is minus the change in kinetic energy. How so? Now we know for conservative system, the change in potential energy is minus the work, and the change in kinetic energy is always the same as work. So from these two expressions, we arrive at that conclusion. Minus the change in kinetic energy is kinetic energy initial minus kinetic energy final, and that is quite simply this subtract that, which is positive 237 joules. And now we can determine the maximum height, which is part D. We shall take the ground level to be the zero potential energy level. So at this point, the potential energy is 237, and that's going to be mass 2 times gravity times h, and you can solve for h, which is about 12 meters. And that solves the problem. Thanks for watching.